Hey guys, it's been a while since I have recorded a video, so bear with me through this disaster. But I thought this review topic called for a video. Hopefully I can explain some things, maybe a little bit differently than I have before, in a way that will help you for this review topic. What we want to do in this review is we want to review finding solids of revolution. So here we have a nice high quality picture that I took out of one of our study guides. And let's work through these problems. First of all, you know it's high class when there's a typo. We go from A to B, but that's okay. We'll keep going anyway. Let's see what it says. The region R is bounded by the curves blah 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 and blah 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 as shown in the figure. So I'm looking at this region right here. And part A says find the area of R. These problems are the easiest ones. All I have to do is I take my top function minus the bottom function and I integrate from this endpoint to the right endpoint. Let's set it up. This is the integral from 0 to 2 of the top function, which is x times 2 minus x, minus the bottom function, which is the cosine of pi x, minus 1. I'm going to go ahead and distribute that negative and make it plus 1 dx. The only way that this problem could get harder is if they didn't tell me what these endpoints were, if I had to figure those out for myself. And it might be a little bit challenging sometimes to figure out which is your top function and which is your bottom function. If this is a calculator question, then I can use my calculator to find the endpoints. I can use the calculator, I can find the zeros or the points of intersection. If this is a non-calculator portion, which this one is, I would have to set the first function equal to the second function and solve for x, and those should give me my points of intersection. Thankfully, on this non-calculator question, they gave us a picture of the graph. Now, to decide which is the top function and which is the bottom function, in this case, I see that I've got a trig function and I have what looks something like a quadratic if I were to factor that out. And I can look at the basic shapes of the graph and see, okay, there's the trig function, that's the one that's on the bottom. And then here's a nice parabola, that's my quadratic function. If you're not familiar with the functions, then what you can do is you can plug in a test value. If I plug in x equals 1, then the function that gives me a greater y value should be my top function, the lesser y value should be my bottom function. Now this is a non-calculator question, and so I will not leave you to do this algebra on your own. Let's work through it. Before I integrate, I want to distribute that. Let's go to the next page and continue here. So this is the integral from 0 to 2 of 2x minus x squared. So I just distributed that x. And then I still have minus the cosine of pi x plus 1. Oh no, what have I done? Come back. Everything's fine. Oh, change the color, that's okay. I'm gonna keep rolling. Now I'm ready to integrate. So this is 2x squared over 2 minus x cubed over 3. That's a 3. To integrate here, I technically have to do u substitution, but it turns out to not be a huge deal. I can say u is pi x, and then du is just pi dx. If I solve for dx, that gives me du over pi. So it just tells me I need to put a 1 over pi out front. So I'm going to put that 1 over pi here, and then I've kind of made a mess of that, so I'm going to move it out of the way and keep going. The integral of cosine is sine of u, and I'm going to plug u back in, which was pi x. If that u substitution had been harder, I would have gone to the effort of making that a separate integral instead of just doing it in the problem here. And I need to evaluate all this from 0 to 2. It doesn't simplify very much. That's okay. When I plug in 2, I have 2 squared minus 2 cubed over 3. The sine of 2 pi, if I think about my unit circle, 2 pi is once around the circle. That brings me back right there. The y value there is 0. So that whole term is 0. And then plus 2. I'll plug it into x. If I plug in 0, I'm going to get 0, 0. The sine of 0 is also 0. And that's 0. That's convenient. So I can simplify this a little bit. I have 2 squared is 4 plus 2 is 6 minus 2 cubed over 3. If I get a common denominator, that would be 18 over 3 minus 8 over 3. And that 18 minus 8 gives me a final answer of 10 over 3. And we did it all without using a calculator. Let's take a look at part B now. The first part B, that one. A solid has base R, as we just found the area of, and each cross section perpendicular to the x-axis. So I'm going to draw a representative cross section there. Is an isosceles right triangle whose hypotenuse lies in R. So if I were to take this and look at it from the side, I just drew that region, and it's a right isosceles triangle where the hypotenuse lies on the base. Right? So this is my top-down view right here, and then this is my side view. Let's call this L, and that's L. So set up but do not evaluate an integral for the volume of this solid. So this is a volume with known cross sections. Step number 1, I sketch my cross section. I label L. Step number 2, I need to find the area of that cross section. To find the area of that isosceles triangle, let me draw that a little bit bigger here. The whole thing has a length of L. This is a right triangle, and then let's divide that in half. If this is isosceles and this is right, that means that this angle is 45 degrees and this angle is 45 degrees. When it's a 45, 45, 90 triangle, when I cut this in half, that 90-degree angle, half of that is 45 degrees. So this is a 45, 45, 90 triangle. If this whole thing was L, then that means that just this length is 1/2 L, which means that this height right here is also 1/2 L. To find the area of a triangle, it's 1/2 the base times the height. And so my area then should be 1/4 L squared. Now what is L? I need to rewrite L in terms of the function. So if I go back and look at my picture here, L could be found by taking the top function minus the bottom function. So I can rewrite this if L is the top function, which was x times 2 minus x, minus the bottom function, which was that trig function. I'm going to run out of room. Here we go. Pi x minus 1. And then for my formula, I need to square that. So L squared is going to be that whole thing squared. That's a 2. Oh my gosh. 2. And then I want to integrate all of those cross sections. So from here, integrate all the way to here. So I'm going to integrate from 0 to 2, all of those areas. And so I'm going to integrate from 0 to 2, all of those areas, which is 1/4 L squared, which is that monstrosity right here. Let's rewrite that on a new slide. That's going to be, I can pull that 1/4 out front if I want to. So from 0 to 2 of x, 2 minus x, that was my top function, minus the bottom function. And I'm taking all of that and squaring it. And that's with respect to x. It said set up but do not evaluate, so I'm going to stop right there. I'm not going to try to factor or FOIL anything. I'm just going to leave it right there. Let's look at the second part B now. It says set up but do not evaluate an integral for the volume of the solid formed when R is rotated around the line y equals 3. So I'm just going to draw a representative slice here. I'm going to take this piece and rotate it around this line way up here. Now what I have to do in my brain is I put my eyeball right here. There's my eyeball, and I'm looking at that point. That's the y-axis right there. That's y equals 3. And I'm taking this shape down here, and I'm rotating it around that point. That's that bar that I just drew there, and I'm rotating it all around here. What I'm creating there is I'm creating an inner radius, r, and I'm creating an outer radius, big R. And then I go back to my picture over here. Big R is the distance from here up to here. Little r is the distance from here to here. Little r is the hole, and then big R is the outside edge of that solid. And so I need to define what those things are. Little r is a little bit easier to see. We'll start with that one. Little r is, if I look at, let's see, another color. If I start at the x-axis and I go up to the function, right? The height of the function gives me that blue distance. If I took this total distance, so this is 3, if I took 3 minus that little section right there, the height of the function, that would give me the remainder, which is that hole that I'm looking for, right? So little r is the entire distance, so that's 3, minus the function. Okay. Then for big R, I can follow the same pattern. Big R should be 3 minus the function, which is the cosine of pi x minus 1. And the fact that this function goes below the x-axis kind of throws me off a little bit. So what I might want to do is I might want to check. Here's how I'm going to check. I'm going to pick a value. Let's say I pick the value x equals 1. At x equals 1, my little radius should be from here to here, and I can see from reading the graph that that's 2. And my big radius should be from here all the way up to here, and I can see from the graph if I go from -2 to 3, then that's 5. Right? So I'm going to plug in a value of x equals 1 and make sure that I get those respective radiuses. So for little r, if I plug in 1, I'll get 3 minus 1 times 2 minus 1. 2 minus 1 is 1. 3 minus 1 is 2. Cool, that one worked. And let's do it for big R. I'll get 3 minus, the cosine of pi is -1, and then minus 1. So I have 3 minus -2, which is 3 plus 2, which is 5. Cool, it worked. I'm happy with those choices now for, ooh, I have other colors. Did you guys know that was there? Oh my gosh, I could have been writing in purple this whole time. Anyway, I'm happy with those radiuses. How did I do that? How did I change colors? What did I... Did I just click on the last one? Well, that's fascinating, you guys. I'm very pleased. Anyway. Now, to find the area of this washer here, to find that area of that washer, what I do is I want pi times the integral from a to b of the big radius squared minus the little radius squared. Can't believe I could have been writing in purple this whole time. All I have to do is plug in numbers now. If I go back and look, my limits of integration are from 0 to 2. I have big R, I have little r, and so I can plug it into my formula. So I have pi times the integral from 0 to 2 of big R and I need to square that, minus little r and I need to square that dx. And that is my final answer there. And I do believe that answers all of that question. Okay, and so we did all that without a calculator. That was nice. Let's go try one more example. Let's look at this one. It says find the volume of the region formed by the curve y equals x squared, the x-axis, and the line x equals 3 when revolved around the y-axis. That's a little bit different now. Let's choose a color, shall we? And these aren't actually that exciting. I can do brown. That's no fun. Orange. Let's do that. I can sketch a graph. So it says by the curve y equals x squared, the x-axis, which is here, and the line x equals 3. I'm just going to pick a region there. So that space that's enclosed is here. And I want to revolve this around the y-axis. Now whenever I'm revolving around a vertical line, this is when everything needs to be in terms of y. And that means that my limits of integration need to be in terms of y. I start here at 0. If this is 3, if I plug 3 into the function y equals x squared, that tells me that line right there is at 9. So my limits of integration are going to be from 0 to 9 in this case. Now whenever I'm revolving things around the y-axis, what I have to do in my brain is I have to take this picture and I have to rotate it 90 degrees. So in my brain, when I rotate this picture, this is now the x-axis, this is the y-axis, and then I have that line x equals 3, and I have this function, and I need to rewrite that function. That was y equals x squared. I need to rewrite that in terms of x, so that is now x equals the square root of y, and I've got this area that I'm rotating around the y-axis. I have to rotate it in my brain like that in order for me to think, okay, what's my big R and what's my little r? Big R, let's go purple again. Big R is from here to here. And I see that it's the same no matter where I am. No matter where I draw that representative slice, big R is the same, and big R is just equal to 3. That's convenient. Little r is from here to here, which is just the height of the function. So little r is just the square root of y. And so when I go to set up my integral, I need the integral from 0 to 9, because I'm going from my y coordinates, right, from 0 to 9. And it's pi times big R squared minus little r squared. And this time I'm going to do it in terms of dy. So very nice. We said that r squared was, or big R, I should say, is 3, minus little r, which is the function. And then I can evaluate that. This one's not too bad to evaluate it. Let me simplify it before I integrate. I'll switch back to purple. I just really like that. So this is pi times the integral from 0 to 9 of 9 minus y dy. So that's pi times 9y minus y squared over 2. That's evaluated from 0 to 9. So this is pi times 9 is 81. 9 squared is 81 over 2. 81 minus half of it gives me the other half. So this is 81 pi over 2. The end. I hope that was a little bit helpful. If it was not, you can always go back and take a look at the original Solids of Revolution videos that I made. Check out those notes, and of course, you can come talk to me and ask questions. I'm glad you were here with me the day that I discovered that I could write in purple. It's a good day.